String theory, it's not a theory of everything. It's not even a complete theory at this point. I mean, it's not even fully defined. Like there are issues within string theory that are still trying to be understood. And this is an active area of research because, eventually what we want to answer is why do we see what we see? And, why is the cosmological constant so tiny? And, these kinds of questions will be very interesting to see if, these are usually very complicated problems, but as we've seen, AI is able to make headway in, which is my worry about where will the new Einsteins come from? Like how will the graduate students be trained in order for them to be skilled at that thing? Maybe they will do it on their own somehow, but we may have to give it some conscious thought.
So the plan today is to go from Einstein to quantum gravity to black holes and to even talk about what AI is doing in the physics today. So hello, Pratik. Welcome to the podcast.
Hi, Ayush. Thanks for having me on the podcast.
Yeah. So, before we can talk about AI and all, so, I want to start from the GR, general relativity. I know the basics of GR, like energy and momentum, that shape the space-time. And the space-time tells matter how to move. We all know that quote from John Wheeler. Space-time tells matter how to move and matter tells space-time how to curve. But I really don't understand what that actually means. So can you tell the story of how physicists went from Newton, how Newton's force of gravity to Einstein's idea that gravity is a geometry in a way people like me can actually picture?
Yeah, so there's this very interesting story that goes all the way from Newton till Einstein, which is that when Newton wrote down his laws, there was a mass that showed up there. So when you have F equals ma, there's a mass that shows up there. And that's what's usually called the inertial mass. But there's also this remarkable fact that the same mass shows up in a different place, which is in the gravitational law. Right? So we have G_m_m over r squared. And that mass a priori could have been something else. This is some intrinsic property of an object, and how it responds to a force acting on it, and how it accelerates is a priori very different from something by which it's attracting other objects, the way the moon attracts the earth. And a simple example of this is the charge, right? Charge is another intrinsic property of the material, which is creating a force by which it's attracting other things. And this has nothing to do with the mass, right? So a priori, it could have been just a completely different quantity that controlled the force of gravitation and Newton's law, F equals ma. But remarkably, we learn, of course, that these are the same quantity, right? So we learn that there's the same mass, and there's a universal fact that all of us fall to the ground at the rate of 9.8 meters per second squared. That didn't have to be the case. And so so it was sort of thought of as a coincidence or something. But very often, like in physics, coincidences often mean something, and you'd like to understand why something is that way. And this is the thing that really got Einstein in the right direction, I think. And once he had discovered the special theory of relativity, it was a natural question of trying to understand a more general theory. And so he reached this idea, which you just described, which is that maybe there isn't such a thing called force at all, right? Maybe there's just one thing. Maybe it's just an object it has its mass and it just moves. And it just moves on some object, on some what he called the space-time, which is like the stage on which the object is moving. And somehow, if we were able to say that there wasn't any force, Newton's first law tells us everything moves in a straight line as long as there's no force. So maybe we should just think about everything moving in a straight line. And so, but of course, we know that things bend and, objects get faster and so on. So how do you explain that? Well, one way of thinking about it is maybe the stage on which things are moving is curved itself, right? So you could have thought about like the surface of a ball or something like that, where what is a straight line on that surface, what is a straight line on the earth is not necessarily what someone far away would see as a straight line. For example, when we go from here to America, we take a very weird curve. Like if you see in your plane map, it looks like a very bent curve. But of course, that's the shortest path on a sphere. And so his idea was essentially you can maybe think about it that way. And when you do that, then you completely get rid of forces. The idea of forces is completely gone. And all you're trying to do is trying to understand straight line motion, but in some curved space. Now it's not so remarkable that there's this one concept called mass. The only thing that the mass controls is, as you said, as John Wheeler said, that mass just tells how the space-time how to bend, and that's it. Once that's done, then this object just moves on a straight line on that. This was a natural explanation of what Newton thought was a coincidence. And whenever you remove such coincidences, what happens is you've reduced the number of parameters in your problem. Right? So Newton had to separately have an inertial mass and a gravitational mass, and then say that somehow these are the same thing. But in Einstein's theory, that just wasn't needed. He just said this mass does only one thing. All it does is curve space-time. And then we just move on a straight line in that. You completely remove the concept of forces. But it has the same physics. It still gives you everything that you had and more, right? So that was enough to explain all the physics that Newton had found, like the solar system, the moon going around the earth, the tides and all of that in some approximation. But it explains even more than that, as we know, like for example, the orbit of Mercury was not quite matching with Newton's laws, and we figured out by this new theory that we can make a better prediction and it actually works well. But the motivation was not to resolve that issue. The motivation was largely aesthetic, as far as I understand. That it was just a matter of trying to understand why is there this coincidence. This is sort of this kind of thing is one thing physicists often call fine tuning. Like there's no reason for these two things to be the same. So there should be some explanation, and we often seek explanations for things that don't appear very natural to us.
So, so space-time is some kind of a thing, I can say.
You can think of it as a stage, maybe. Like maybe that's the natural way to say. It's like the way I like to picture it is maybe if you think about a globe, you can think about ants living on a globe, right? For them, space-time is just the surface of that globe. We may think of that globe as embedded in a higher space and we can see it and so on. But an ant who cannot jump can only ever walk on that two-dimensional surface, and for them, that is space-time.
Yeah.
It's where they're living. Except, of course, here we have to imagine time, but that's just an added complication. That's not so important. The important thing is that maybe the non-trivial part was to think of things as sort of curved in some way, as opposed to what we think of as flat space. In our flat space, we can draw triangles with straight lines and they form the total sum of angles being 180 degrees. This is not true when you have curved space and so on. So the hard part was, making that jump, that somehow we're living on something like that.
Yeah.
Even though we can't look at it from outside, it's just intrinsically we're living on something that is like the surface of a globe.
So can you think like space-time can have mass?
Space-time also has mass in some sense. So let me just try to explain a little bit what we could mean by that. So once you learn that space-time is a field, fields have excitations, right? So the thing that we think of as light is an excitation in the electromagnetic field. And moreover, with quantum mechanics, we understand that these are just photons. Photons are particles which are excitations of the electromagnetic field. Just like that, now once you have a field, once we think about this space-time as a field, there will be excitations of the space-time itself. These are what, one may call gravitons, or if you think about it more in the analogy with light, these are gravitational waves, right? So this is the thing that LIGO detected, and now we've gotten really good at detecting black hole mergers using these waves. It's like looking with some different glasses. These are similar to light waves, but they're the analog of light for the gravitational field itself. And those themselves carry energy. So space-time itself can carry energy in the sense that light carries energy, right? Light is just an excitation of electromagnetic field. Once it's generated by some material or atoms or something, it just travels on its own and it just carries that energy. The same sort of story holds for space-time itself, where space-time can maybe, something like a black hole merger where there's mass and, there's something happening, can generate gravitational waves. But once they're generated, they just carry off this energy in their own directions. And so they do carry energy. So the space-time itself carries energy in terms of these excitations. So that's the sense in which I would say it has, maybe you can call it mass, but perhaps you should say energy, which is sort of equivalent by E equals mc squared.
Yeah, you mentioned fields, and if you go back in the history, Maxwell had a theory of electromagnetism, and
Yeah.
Einstein took Maxwell seriously because electromagnetism already had the deep connection with light,
Yeah.
light, fields, relativity. So when you look back at the physics history, do big breakthrough usually come from physical picture first, or like from the math first? Because Einstein was like,
Yeah.
first he imagined like something in head and then write the equations. And at the other hand, David Hilbert was like, let's write the math and we will imagine the physical picture later. And we can also
Yeah.
take the example of Paul Dirac. He just said that mathematical beauty is everything. I don't
Yeah.
remember the
Yeah.
actual quote, but it was something like that.
Yeah. Yeah. This is actually a very interesting question. And I think it's something where sort of both are true. I mean, there are physicists who have a certain way of thinking, and there are physicists who have a different way of thinking, and they can sort of coexist, and it's sort of valuable for us to have both kinds of thinkings. For example, I mean, already in the context of electromagnetism, I mean, Faraday had this picture of, thinking of flux lines and so on. Like he had this picture which it sort of complicates the maths, and sometimes you want to wonder, like, why would someone think about
Yeah.
field lines and so on? Maybe you just write down Coulomb's law and you're sort of done with it. But it ended up being a useful way of thinking about things. And sometimes a physical way of thinking about things is genuinely valuable. But at the same time, sometimes just pure aesthetics, pure I mean, you still need to be guided by some physics, but sometimes you just want to appeal to some sort of the rigidity of the laws of physics, or the beauty of nature, about how it works. And I think they all come together. Like for the theory of relativity, it was crucial that Michelson and Morley did this
Yeah.
experiment where they realized that, I mean, at that point, what people thought was just like, light. I mean, just like sound travels in any medium, you need some medium in which light is traveling. And so people called this the ether, because people had done experiments where they just sucked out all the air from a region and you could still see light propagating. So they were like, oh, even after you suck out all the air, maybe something is left. That's the ether. And so people really believed in this ether. And what Michelson and Morley were trying to do was discover some properties of this ether. And, what they discovered was consistent with just not having an ether. It, of course, took time for this lesson to sort of seep in. And it always takes time, because it was a prominent view of the time. And so people believed in various different theories of the ether, and they wanted to rule out different properties it had and so on. And so that was a crucial experimental input, which would have guided people back then. At the same time, the Lorentz transformations, which are sort of the fundamental thing in the theory of relativity, were almost written out of, no purpose really. I mean, Maxwell wrote his laws, and, it was just discovered that it has these symmetries. You just transform the electric and magnetic field in a certain way, which includes velocities and speed of light and so on. And magically, it's invariant under those changes. This, in modern language, is what we call Lorentz boosts. This is basically going to a moving frame where, all sorts of special theory of relativity effects show up. But this was basically the first place where it was discovered, and it was discovered before the special theory of relativity with
Yeah.
no real purpose. It was almost an aesthetic thing. And both of these things, I think, would have guided Einstein in leading to the theory of relativity. And so, it's like there's different ways of thinking in physics, and they're all useful. Like, different directions give you different inputs, and they're all valuable. Dirac, of course, as you pointed out in your example, was a very strong mathematical physicist, and as were many other people of that time. But there were other people of the time, for example, Fermi, who had a very interesting, like, order of magnitude way of thinking about things. And, like, these are very different skills a priori, and they're both valuable.
Yeah.
Like, these both contributed to the development of quantum mechanics.
You can look at the
And
Feynman
yeah, I mean, maybe
Feynman
yeah,
Feynman
yeah, sorry.
diagrams.
Exactly. Another brilliant example is quantum electrodynamics. So, as we discussed, in the theory of electromagnetism, we have light and so on. And people had tried to make this work in a quantum mechanical way over years and ran into all sorts of problems. Like Dirac himself was one of the first people who did this. You run into infinities, and I can say more about that if you want. But it seemed like a sort of inconsistent theory until it was made sense of much later. But it was made sense of by multiple people around the same time in very different ways. So Feynman had these sort of picturesque ways of working with things, where he drew these diagrams and sort of thought about light and interactions with matter in terms of diagrams where light comes together, meets an electron, and some things like that happen. It was a very visual way of thinking about things. And on the other hand, Schwinger and Tomonaga had different ways of thinking about it, which were, coming from very different math, and they were sort of tedious also, but they were also correct. And these ended up being equivalent.
So,
Um,
uh,
yeah,
Dyson, I think, connected all of them. Am I right?
exactly. And Dyson eventually connected them, and you see that it's the same physics presented in different ways. So there's the Feynman diagram way of thinking about things, but in modern physics, we often also use things like Schwinger parameters, which are useful ways of thinking about quantum field theory, and even in things like string theory. So even though it's it's at a higher level of sophistication, we still use methodology which was developed then. There's the so-called Schwinger-Dyson equation, which is also used a lot, which are sort of maybe different ways of thinking about things. But these are complementary. Often these things are complementary, and it's valuable in physics, I think, to have these different ways of thinking. Even today, in today's world in physics, I think there are physicists who are extremely mathematical and who think in a certain way, which is very rigorous and very, very, I don't know how to call it, like maybe structured or something like that. But there are also physicists who have a more intuitive way of thinking about things, who have more physicsy arguments, who have more perhaps Feynman-like visual thought processes. And humans are very different in this way, and everyone can contribute something in that way, because what one picture may find easy might be difficult in another way of thinking about things. And like there's a classic example of general relativists arguing forever about whether gravitational waves are real or not. And it's for good reason. Like when you write down these things, I mean, general relativity has this so-called thing called diffeomorphism invariance, where you can get yourself confused about whether things are real or not. Maybe it's just a diffeomorphism, maybe like it could be just I'm using some funny coordinates to write something, and is this really a physical thing? And Feynman had this very simple physical argument, which was, you just have a gravitational wave pass through some object like a set of beads, and it heats them up, and that's it. Like, it's a very different way of thinking about it. Relativists were thinking about it from a different perspective, and that was valuable for other things. But here there was a simple situation where this was useful. So I think we should keep that in mind. We should keep it in mind that there are different ways of being good physicists and different ways in which people can contribute valuably. And there isn't like one sort of role model. Like, there are many role models here, and there's many different ways of succeeding,
So,
which we should keep in mind.
if I take the example of Dirac, do you think we would have discovered antimatter without if Dirac had not given the equations?
I'm almost certain that we would have discovered it. How long it would have taken to theoretically make sense of it, I'm not sure. So, as you know, like in Dirac's story, like he just wrote down some equations to describe the electron, and it felt like he had this opposite charge thing which was showing up necessarily, and he couldn't make sense of it. He thought, okay, there's a Dirac C and so on, and it was a puzzle for a while. But I mean, of course, like experimentalists went out and found the positron. And even if Dirac hadn't written his theory, I'm sure experimentalists would have done that experiment.
Yeah.
Right? It seemed like a very natural experiment to do. And, experimentalists keep trying things of this type. I'm pretty sure they would have discovered something with positive charge that's equal to the electron in mass. And then it's a question of how people would have, made sense of it. I'm sure, like in this situation, like you can figure out all the quantum numbers by simple experiments, and then someone would have had the idea that okay, we should pair this thing with the electron. It didn't have to be the case that Dirac had written this weird theory beforehand and made a prediction. I'm not even sure he really believed in that prediction. But it sort of obviously fit together after we had the particle, and we kind of understood quantum electrodynamics as it is. But this is a situation where it could have gone either way, and I think that is just a historical coincidence that he came up with it before. It could very likely have been that the experiment came first.
So there is also theory of antimatter, which says that Feynman and other made that famous, like the particle is negative because it's moving backward in the time.
Right. So there's this thing called and it's actually with Wheeler.
Yeah.
It's called the Feynman-Wheeler absorber theory or something like that. Yeah, they had this whole thing. As you said, like Feynman diagrams, when we draw Feynman diagrams, when we draw it for the electron and positron, we often draw like arrows in opposite directions. And this probably goes back to Feynman, who thought of them as basically like electrons going backward in time. And there's a sense in which that's true,
this movie Tenet, where they have shown, people going backward in time. So I just connect both of these two. Yeah.
I see. I haven't actually watched Tenet. I've heard that's an extremely confusing movie. I haven't watched it. But in physics, like, okay, at least classically, once you know the initial data on any surface, like meaning that if I tell you the position and momentum of every particle right now, you can evolve that data to the future or past or whatever, right? So in some sense, things exist all the time. There's a sense in which we think of ourselves as going forward in time, which is essentially that there's only one thing that tells us that there's an arrow of time, which is the second law of thermodynamics. The second law of thermodynamics tells us that entropy is growing. And, because entropy is growing in a particular direction, that gives us a sense of going one direction in time. If things looked the same going forward as backward, then there wouldn't be a sense in which we would remember the past and feel like we're moving to the future. Like, when we're going to the future, it feels like, we learned some things about the past and now we're knowing new things. But it would have never felt like that. The only thing in our universe that tells us that there is a direction of time is basically the fact that we had a very low entropy Big Bang, which leads to us having this growing entropy over time, and we experience time going forward. But of course, there's nothing fundamental about that. That's something particular about where we find ourselves, right? The universe started from this low entropy situation, and now we can experience it this way. But there's nothing fundamental in the laws of physics about forward in time or backward in time. In fact, there's this famous symmetry of physics called CPT, which includes time reversal. So you can just reverse time, and along with some other things, and the laws of physics look basically the same. And so you might as well have this Feynman picture of electrons. Like if you just flip time, the direction of time, you can just write all the laws of physics in the same way, except the only thing that happens is the electron swaps with the positron.
Yeah.
So that's a valid way of thinking about it.
So what kind of physicist are you? Are you more like a visual or physical picture type of physicist, or like mathematical or equation, or maybe something else?
It's yeah, I mean, that's a very coarse description, of course. Like, of course, within that, there's very subtle differences between different physicists and what sort of strengths they have. I certainly don't think of myself as an extremely mathematical physicist. That's not my strength. But I feel like one of the skills that I find useful is trying to make connections. I think of myself as a very interdisciplinary person. So as you described in the beginning, I work on quantum gravity, but I try to bring in tools from quantum information theory, from condensed matter theory, other fields of physics where similar things have been thought about, and maybe you can apply ideas to quantum gravity. Bringing together such ideas and making such connections is what I like doing, and I feel like hopefully that is somewhat my contribution. And this it's not just me. There's many such people who are working in this field of trying to bring together ideas from quantum information and quantum gravity. So there was a whole field which was called it from qubit. The idea being, space-time coming from just quantum mechanics. And there was a tremendous amount of value that was added to our understanding of quantum gravity from just thinking of it from a quantum information perspective. There are often questions that quantum information people ask that quantum gravity people would have not usually thought about. And these things have been useful in trying to understand quantum gravity. And vice versa as well. Some things look very natural in quantum gravity, and teach you new things about quantum information. So things go both ways, and I feel like what I really enjoy doing is trying to make such connections, trying to bridge these different topics together.
So you are in the middle of those things.
Yeah.
Yeah. So you work with Yasunori Nomura. What did you learn from him about how to choose good problems?
Yeah, actually, my advisor Yasunori he had a very interesting trajectory.
Yeah.
He was a particle physicist. He was a hardcore particle physicist working on the LHC, and he had written interesting theories of the Higgs and so on. And once the LHC turned on, Higgs was discovered and so on. He was quite in the limelight. But when the Higgs was discovered, there was this idea floating around. So let me just give you some background.
Yeah,
there's this famous problem with the Higgs called the hierarchy problem. The hierarchy problem questions, why is the Higgs so light? Okay, so what is the natural scale in which we should measure these things? Whatever the scale of the problem is, right? So the scale of the problem, I mean, in our universe, there's basically one Planck scale, which is the fundamental thing. And typically, in the absence of things like supersymmetry, scalar objects. So the Higgs is a spin zero object, and such things usually get large corrections to their mass, and they end up being close to the scale that's in your problem. So say the Planck scale. If you add supersymmetry, then some cancellations happen, and then it's allowed to be light. But in our universe, there is no supersymmetry, right? At least at the level at which we've probed it. The LHC did not discover any supersymmetry. So at the very least, what one could say is that there's some supersymmetry that gets restored if you look at high enough energies. But at low energies, certainly supersymmetry is broken. And so you would expect that the Higgs would be at the scale at which supersymmetry is restored. This is what people were looking for in the LHC. Okay, so what people wanted to see was, they wanted to discover the Higgs, of course, but they expected that if supersymmetry was the reason that the Higgs was so light, then you would see a whole host of particles very much around that energy. Now, this wasn't to be the case. This wasn't discovered. Like, no other particles other than the Higgs were discovered around that energy. Other than the top quark, which was known before, and that was already part of the standard model, but none of these supersymmetric partners were discovered. And so people started to think about other ideas for how this could be. And one of the things that Yasunori was thinking about was the so-called multiverse.
Oh, yeah.
So multiverse is this very fascinating idea, which perhaps like science fiction has explored a lot, which is the fact that there are really many. Yeah. So we see this in the movies a lot, and it's very fun to think about, where you have many different universes, and in this context, what we imagine is many different universes with many different physical constants. So maybe the electron mass is slightly different, maybe the charge is different, maybe there isn't an electron, maybe there's a different set of fields that shows up, that kind of thing. And the idea was that perhaps what's happening is that is the explanation for why we see a light Higgs. So just to make an analogy, back in the day, Kepler wanted to explain why the planets are where they are. Okay, so at that point he had seen 5 planets, I think, and so he wanted to explain the locations of these planets in terms of what he wanted some fundamental law for where planets should be. And because there were 5 at that point, he thought these are related to the Platonic solids. Okay, so there are 5 Platonic solids, cube, octahedron, and so on. And somehow some property of them would tell you where the orbits are. So he came up with some theory of this type. Of course, now we know what the explanation for why we are where we are is. It's because there are just so many planets, And if we were either too close to the sun or much further away from the sun, we wouldn't exist, right? We want some decent conditions for humans to exist. And so the Earth is where it is. It's called the Goldilocks zone, where it's not too hot or not too cold. And we see ourselves there because we exist, right? Otherwise, we won't exist, and we won't see ourselves there. So this is the kind of explanation which is often called the anthropic explanation, which people were seeking for the Higgs. So the idea was, if we imagine a multiverse of theories, where you have different properties in different universes, then we would only ever see ourselves in universes which are compatible with us existing. Right? If the mass of the Higgs was very different, it's possible that our universe would look totally different. Maybe chemistry wouldn't be possible as we see it. Right? Maybe the masses of the nuclei won't work out correctly. Maybe the energies of the nuclei won't work out correctly for us to exist. This was the kind of arguments that were being made. So this is sort of this multiverse type of theory for predicting where the Higgs boson lies, and it achieved some level of success. And so this is the kind of thing that got him thinking about quantum gravity. And so he was sort of an outsider viewing it from this different perspective. And I think the advantage that some particle physicists had was the fact that they had the LHC. Okay, so particle physicists were very much after explaining the universe. This was like they had this pinpointed reasoning of they only ever cared about explaining the universe. Anything else was just auxiliary. So I feel like he had that sort of spirit to him. He wanted to only ever explain things in our universe. Very often, I mean, as opposed to just writing broad frameworks of theories which will work abstractly and stuff. I mean, he really cared about physical questions. So one of the problems that got him interested for that reason was the black hole information puzzle, where it was really a question about our universe on scales that we can observe. Right? There was something about doing an experiment in our universe where I can fall into a black hole and ask, what do I see? That seems like a very physical question. And so he was always after these kind of physical questions, as opposed to more abstract mathematical questions. And I feel like that got imbibed in me a little bit from him.
Yeah, so you mentioned he was working something to Higgs field. So people get confused by Higgs field and Higgs boson, because Higgs is coming from Peter Higgs and boson is coming from Satyendranath Bose. So can you a little bit explain between the difference between these
So
terms?
I can say a little bit about that. In quantum field theory, maybe we can take the example of electromagnetism just to get started. So in electromagnetism, we know that there are fields, which is the electric field and magnetic field. Field just means that there's some value it takes everywhere in space, which is different from point to point. What we learned in quantum field theory is that these things are quantized. So excitations of this field are quantized in the sense of how light is quantized into photons. Okay, so light looks like some continuous thing that's traveling, but if you look carefully enough, it's really packets of photons, each of them carrying some quantized amount of energy. So there's discreteness in it. Now, so every particle in our universe is secretly the excitation of some such field. Okay, all fields like the electron is an excitation of the electron field, and so on for every particle that we have. And so similarly, the Higgs boson is a particle that is the excitation of the Higgs field. Right, so the Higgs field is something that permeates everywhere in the universe, and it can have excitations here and there. Those excitations will be quantized, and each of those excitations is what we call a Higgs boson. The word boson is to distinguish it from fermion. All things that carry integer spin, like 0, 1, 2, etc., are bosons. So the Higgs carries spin 0, the photon carries spin 1, the graviton that I told you carries spin 2. These are all bosons. Every other thing that we see, most of the other things that people would know about, like electrons, protons, and so on, these are all fermions. They all carry spin half.
Fermi-Dirac
So in that sense. Yeah, so they follow Fermi-Dirac statistics, which is different from Bose-Einstein statistics. These have drastic consequences for how the field behaves, and this was really what this was the major contribution of Bose.
Yeah.
Really, he realized that there was this funny thing that was happening for integer spin, and Einstein was very kind in appreciating what he just received a letter from SN Bose, and he immediately understood that this was of great value. And today there's a lot of things that have been understood because of Bose-Einstein statistics. For example, superfluidity. It wouldn't exist if we didn't understand Bose-Einstein statistics. So it's a crucial contribution from Bose.
So, where does the Einstein story continue in your work? Like in quantum gravity
Yeah.
and holography, are we still thinking geometrically, or does
Yeah.
geometry itself become something that has to emerge from deeper quantum information?
Excellent. So good. So yeah, so the natural question, once Einstein came up with this beautiful theory of general relativity, of course, almost around the same time, quantum mechanics was being developed. And quantum mechanics was this idea that, as we said, there are fields, but they have excitations which are discrete in some sense. So this idea was then applied to the other forces that we understood. And we've had great success in explaining electromagnetism that way. Like we understand photons, and we also understand the nuclear forces this way. So there are similar particles that exchange nuclear forces, and so a natural question was to ask, okay, what about gravity? Gravity is a force that we feel. We'd like to explain it in the same language. It should also be a quantum mechanical theory. If then we would have this complete theory, which is all quantum mechanical, and it describes all the forces at once. Now, this actually runs into issues, and even though formally we can talk about a graviton at some level of approximation, it's hard to make it a complete theory. And this is something that has happened previously in physics. So even before we had the current what's called the standard model of particle physics, this is the complete quantum field theory that describes electromagnetism and the nuclear forces all at once. Basically everything except gravity is explained by this thing. This theory is complete in the sense of what's called renormalizable. So this is a theory which doesn't need infinite amount of experiments in order to make predictions. So you make a finite number of experiments. It fixes the parameters in this theory, and then you can make as many predictions as you like. Okay, so it's very powerful. When you try to do this for gravity, when you just try to fit in gravity into this framework, it fails. Okay, it becomes what's called non-renormalizable, meaning that for every additional experiment, you'll have to put in more data and so on. And it's not a complete theory. It signals that there's secretly a better underlying theory, which would give you something like quantum gravity. Now, in the case of the nuclear forces, this had happened before, and people had discovered the standard model of physics by trying to complete what was that time a non-renormalizable theory. But in the case of gravity, people tried this for a long time and didn't get much success. So it seemed to be much harder than what was happening for the nuclear forces. So this made people try other things, and almost by coincidence, people discovered ideas like string theory, where there happened to be something like a graviton. It seemed to be what was a complete theory. It was a renormalizable theory, and it included a spin 2 excitation, which you could interpret as the gravitational field, the graviton. And so this became a sort of different direction in which people tried to pursue quantum gravity, and it eventually led to this idea of holography. So this is this beautiful idea that if you want to describe gravitational physics in, say, a ball, you only have to describe it in terms of non-gravitational physics on the surface of a ball. Okay, so we live in three-dimensional space and one dimension of time. So the idea is that in order to describe physics of our universe in a quantum gravitational language, you can describe it using a non-gravitational theory that lives on a surface, which would be a two-dimensional space and one dimension of time. That seems like a remarkable fact, right? So in quantum field theory, we had no such reduction number of dimensions or anything like that. But in quantum gravity, we have concrete examples that come from string theory, the so-called ADS-CFT correspondence, which your listeners may want to know about, which concretely tells us that there's a very sharp sense, and we have these examples where there are some completely different degrees of freedom that live on the boundary of space-time, and they interact in some complicated way, but their dynamics is equally well represented by the physics of gravitating objects in one extra dimension. So you can imagine the way we think about this is usually like a soup can. Okay, so soup can has it's like a cylinder which is filled in with soup. So if you want to describe the soup, it's as if you can describe the soup, which is basically the gravitational physics, just by looking at the boundary of the can, just from the can. From outside, you can basically describe it completely in terms of a theory that lives there. This is a very complicated rewriting. Okay, so the theory that lives on the boundary of space-time looks nothing like a gravitational theory. It's actually a very complicated quantum field theory in the examples that we know, which is strongly interacting and includes a large number of degrees of freedom. And nevertheless, its dynamics sort of magically reorganizes into a structure where in the bulk of the space-time, you see very simple gravitational physics, weakly coupled Einstein's equations, which is a remarkable fact.
What does this weakly coupled mean here?
Yeah.
Weakly coupled.
Yeah. So let me say, yeah, good. Most of physics, there's a famous quote actually, which says that most of the career of a physicist goes about basically applying the harmonic oscillator. Hopefully, people know what a harmonic oscillator, just a spring, at higher and higher degrees of sophistication. So the harmonic oscillator is actually a very simple model, which is completely solvable in quantum mechanics. Now, it turns out when we try to do quantum field theory, there's a complete analog of harmonic oscillator, which is called the free theory. Free theory is basically where particles just cross each other, without hitting each other or interacting in any way. So this is like basically particles that are zero coupling. So they don't interact with each other, they just freely pass through each other. There's a sense in which this is precisely like the harmonic oscillator, and it's exactly solvable. This we know how to do. Now you can ask, what do I do if I turn on a little bit of coupling? This problem gets hard. Okay, in general, it's hard to solve. But if the coupling is small, then what you can do is what's maybe familiar to people under the name of Taylor expansion, right? So when you have a function, you can expand it and then look in the neighborhood of the point in a series. And then you can systematically compute things in a series. This is what's called perturbation theory in physics. Okay, so you start from some theory that you completely know how to solve, and then you perturb around it and sort of systematically include corrections. When you do this and you can do this if you're near enough to that point. Okay, so the point here is the free point, which is basically zero interactions. So meaning that if you have a small amount of interactions, you can move slightly away from this free point and still make some predictions about this slightly interacting theory. This is something that's well within, like, this is like bread and butter for physicists. Okay, so all these beautiful calculations that have been done about quantum electrodynamics. There's this famous G-2 that matches up to 10 decimal places and so on. All these successes have largely been attained from perturbation theory. A lot of these successes have been, not all, but most of them have come from perturbation theory. And Feynman diagrams is a way of reorganizing perturbation theory. Okay, so all of this is really that, and that's what we know how to do. So for most problems, all we can really deal with is weakly coupled systems where we can do perturbation theory, meaning that the interactions are small enough that we can deal with it by thinking of it as a sort of free theory and then just moving away slightly. A strongly coupled theory is where things are strongly interacting. The interactions are big enough that we cannot think of it as a small deformation of a free theory. This is, of course, a very interesting thing And this happens a lot in physics. Superconductors are a classic example of this kind of thing. The strong nuclear force is an example of this kind of thing. And there's a lot of beauty in these kind of things, but of course, it's difficult to solve. Okay, it's difficult to often solve and make predictions. In string theory, in these examples where I'm talking about, this complicated theory that's describing quantum gravity, there are some beautiful theories which include supersymmetry and so on. But because of such amount of supersymmetry, there's a certain tractability to them, even if they are strongly coupled, meaning that there are strong interactions. Okay, there's no sense in which it is anywhere close to a free theory. Okay, and nothing like a harmonic oscillator. But nevertheless, there are other techniques that we can use to actually solve such systems. But they look very complicated. Okay, they look something like you have to be a specialist in this to understand how this thing is working. It's not very basic physics, and so it looks very complicated. So in that sense, it's a very strongly coupled system. But somehow, and what's happening is the strongly coupled system living on the boundary of the theory somehow describes gravitational physics in the bulk, which is actually weakly coupled, meaning that in the bulk of the spacetime, all you have to do is think about Einstein's equations with small values of g. Okay, g is the gravitational constant, Newton's constant, which controls how much things interact gravitationally. And you can set this to be a very small value and treat it like a small deformation of a free theory. So magically, a very weakly coupled theory, which is very tractable and very much in our ballpark as physicists, is exactly dual, or is computing exactly the same things as a strongly coupled theory which is living on its boundary. The nice thing about this example is the strongly coupled theory is non-gravitational. So it doesn't give us all these complications about trying to find a theory of quantum gravity and so on. We just understand that theory in principle. It's just quantum field theory. We understand that framework very well. But in the bulk of the space-time, what we have is a quantum gravitational theory. It's something for which we don't have a completion. It's for something we don't have a complete theory of quantum gravity. But now, because these two are the same, any question you want to ask about quantum gravity, all you have to do is translate it to the boundary theory, to this theory that's living on the boundary. And then in principle, you can answer it there. Okay, so it makes some predictions for how the quantum gravity theory functions.
Yeah, so everything is connected to, I can say, geometry or topology. I always get confused between geometry and topology. Geometry feels like distance, as in curvatures, shapes. And on the other hand, topology feels like what stays the same way when you stretch or deform something. So in modern physics, especially like quantum theory, quantum gravity, or string theory, why do both matter?
So geometry is being described because we're interested in understanding space-time itself, right? So we want to describe the geometry of that. Now, geometry in some sense contains topology, in the sense that geometry is interested in distances between points and sort of the structure of space-time and so on. But of course, topology is an interesting way in which space-time can be different. So here's an example. A simple example is a sphere, right? So if you take a sphere, it's just, we understand what a sphere is. But of course, you can have also what's called a torus, which is like the surface of a donut. The surface of a donut has a hole inside it, right? So this geometry is very different from the spherical geometry. And similarly, you can have things with arbitrary number of holes and so on. And what topology usually changes is sort of global properties of the physics of the space-time and things like that, global properties. Geometry usually and colloquially is talking about local properties. Okay, so when we talk about just local distances between points or things of that type, velocities and so on, that is often described just by standard geometry. So in the local neighborhood of any point, we can always just think about it like flat space. Right? We can just think about it like flat space, or at least topologically like flat space. We can have some coordinate chart on it, and we can just ask about distances between points and so on. Like if you want to imagine something like that on the sphere, we can have a chart which is on the northern hemisphere and a chart which is on the southern hemisphere, which sort of need to be patched on somewhere. But on that entire patch, you can just compute distances. This is the whole reason, we can draw maps at all, right? So locally, geometry is going to tell you about all these distances, but globally, it's important that we need two patches, right? You cannot ever have a completely flat patch which will fill the full globe, right? You'll always have to excise out the opposite pole. Okay. um, right, so this is why, like, atlases aren't perfect representations of globes. If they were, then there would be something, topologically the same about these two things. So 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 this topology is telling us about some global property of things which we may be interested in separately. So these also give rise to very interesting physics, and this is very interesting in the context of condensed matter, especially nowadays, where properties earlier used to be mostly thought about in terms of local things. So we would, whenever we write field theories for materials and so on, we would normally think about local properties. But global properties can also be very important, and topology is the thing that encodes these things. And I would say it's like relatively, I mean, maybe the last so many decades is when topology has really made an entrance into these things and taken over, and people have realized that there are interesting things that can be found by thinking about things in terms of these global properties like topology.
Can we say that most of the physics is just geometrical?
Is geometrical?
Yeah. Yeah.
In some sense. Okay, if string theory were to be true, then it's certainly geometrical. Okay, so string theory is this putative theory where everything is just written in terms of a sum over geometries of this string. So string is basically the string is the basic excitation of that theory, which propagates and the various kinds of interactions it can have and the various kinds of string modes that you can have are representative of all the excitations that we see in our universe. That's the thing string theory is after. Okay, so other than just the graviton, it would also like to describe the electron, the Higgs boson, all of those things you'd want to just come out of the interactions of a string. Now, in that context, it's just completely geometrical. Even if we forget about something like that, since we don't have a full theory of everything, there's certainly a sense in which quantum field theory is pretty geometrical. I mean, we always think about things in terms of their symmetries and their structures, which borrows a lot from the geometry, like geometric fields in math. Strictly speaking, we often talk about space-time as our geometry, and then these other fields are sort of living on that geometry.
Yeah.
But you can just think about that as more geometric things on top of this geometry. So secretly, it's all geometry in that sense.
Yeah.
So it's in some sense, it's some unified geometry. Yeah.
Yeah. Most of the theory in physics are just geometrical, from
Yes.
electromagnetism to Einstein, general relativity to QFT, and now string theory.
Exactly.
So string theory has this public image. Some people call it the theory of everything, and some people say it is too mathematical or too far from experiment. From the inside of the field, what is actually string theory today is useful for?
Yeah, I actually I myself have changed my opinion on this a lot. So I'm completely sympathetic to the people who think it's too mathematical and so on. Because when I was an undergrad at IIT Kanpur, there was this general vibe that string theory is some weird thing these people are doing. I don't know. It was sort of we were sort of dissuaded from even thinking about those things. And I actually remember reading a book which is by Lee Smolin. It's about basically arguments. It's an entire book that's written about anti-string theory. It's about how string theory has screwed up everything essentially. I thought, oh, okay, these string theorists are really bad or something. and then I went to do my master's at Perimeter Institute in Waterloo. And there were some really good string theorists there and so on. And we had some very good courses as well. And it sort of didn't take much to be convinced that there was some value in it. It was just beautiful for one, but that of course isn't everything. I mean, beauty isn't everything. That then you could just say it's some theory of math or something. But there were some amazing things that string theory was doing, which we weren't able to do in any other way. And for instance, one of the things that really impressed me was being able to compute the black hole entropy, like being able to explain the entropy of a black hole in terms of counting some number of states. In thermodynamics, we can give entropy just as some meaning in terms of heat and so on, but we understand in physics that an entropy always has a meaning as some statistical microstate counting of the system, like how many states are consistent with the same microstate that we observe. And this is something that string theory managed to do in certain examples. A lot of it comes from the work of Ashok Sen, of course, who's been a huge contributor to this field, and a lot of other work in India which has contributed to this thing. And it's sort of remarkable that this could be even done. I mean, it's done in very limited settings, like it requires supersymmetry and so on. But in any theory of gravity at all, I mean, there's nothing that I've seen that matches that. The other thing which totally impressed me was this ADS-CFT correspondence. Okay, I mean, this idea of holography existed before the ADS-CFT correspondence. It existed sort of simultaneously with string theory, and it was an argument that anyone could have made. Okay, I mean, of course, it takes some insight to do this, so you have to be Gerard Toof to make it, or Lenny Susskind. But it was a very simple argument. It just relied on the fact that the black hole entropy goes like area and not volume. Okay, it was a simple insight which has radical consequences. And this idea existed, but string theory somehow remarkably gave you a very tractable, concrete example where you just see this and it's visceral. Like it's like you can compute things on both sides; they match exactly. You can do all sorts of detailed checks on it. It teaches you various new things about how quantum gravity works, these geometric where this geometric description of gravity is even coming from. It's coming from some very complicated description of this field theory that, as I was saying, was strongly coupled and has large number of degrees of freedom and so on. And it just felt like magic to me at that point, that you could explain so many things even though it's in a limited setting. And those insights came from string theory, and many of those insights don't actually, like, there are insights which apply to the real world in some sense, like insights about black holes, insights about what one can say just generally about, for example, as I was telling you earlier, like what I've been interested in is this interdisciplinary sort of way things work, and predictions for how fast how chaotic things can be, just as general quantum systems. Okay, so anyone studying quantum systems could have asked the question: is there a bound on how quickly things can scramble? So when we think about chaotic systems, it means if I start with if I put some coffee and milk together, they can be separated, but then I stir it a little bit and they sort of mix together. So you can ask about how fast this mixing dynamics can be. And this isn't a question someone asked, and this isn't something they had an answer for. But by studying black holes, string theorists or whatever people interested in quantum gravity came up with an answer which you can just prove completely independent of string theory or quantum gravity. It's a fact that's true of any quantum system, and it came out of trying to study black holes in this context of ADS-CFT. So even if one may, I mean, in the public, I know that there's a lot of this discussion, and so I usually shy away from actively engaging again. Yeah, I usually don't actively engage with people who are trying to make these views. But my opinion on this is, like, you may deny. So here is something where you can actively criticize string theory. String theory so far has not been able to has not been able to. I mean, certainly it's not a theory of everything. It's not even a complete theory at this point. I mean, it's not even fully defined. Like, there are issues within string theory that are still trying to be understood, and this is an active area of research. Moreover, this ADS-CFT correspondence that I talked about is quite different from our universe as we see it. Okay, this ADS is what's called anti-de Sitter space, which corresponds to having a negative value of the vacuum energy, the dark energy that we see in the
Cosmological
universe.
constant.
Our dark universe, yeah, the cosmological constant. And our universe has a positive cosmological constant, has positive dark energy, which sort of tends to repel things.
Yeah.
It tends to accelerate things away from each other, as opposed to a negative one, which would bring things together.
Yeah.
So this is quite different. And, there are still lots of things to be understood about our current universe. But these are active problems. These are things that string theorists think about. It's not like string theorists don't care about it. Or it's not like they're just interested in, pushing their agenda on this theory as opposed to trying to explain the universe. All string theorists I've met have, really want to explain the universe. And so even if you deny, so sometimes the discussion that's made is there's some agenda or something. So that I think is just, I just don't know how to defend that. I mean, it's just way too far from the truth to even, engage with. Even if you deny quantum gravity as a goal worth pursuing. Okay, so this is another thing that I've heard a lot around, which is you may want to say something like, okay, who cares about quantum gravity? Maybe it shows up at the Planck scale. I don't really want to know. I want to know something that I can do in my lab. I want to know something that is within our universe, which we can test and build an experiment for, and so on.
Yeah.
The fact that thinking about things in terms of string theory or quantum gravity is helpful for even making predictions for that, right?
Yeah.
Like an example being this bound on chaos that I talked about. It's something that an experimentalist, like a person doing condensed matter, can go to their lab and just try to do an experiment on and try to see. It's remarkable, right? Even if you think this goal is not worth pursuing for itself, it's certainly just the amount of connections it has made tells you that there's something right about it. There's something useful about it.
Yeah.
It's so here this was an example where it's useful for people thinking about quantum systems in general, condensed matter, quantum information, and so on. Other examples include things like trying to understand entanglement. So entanglement, quantifying entanglement in a many-body theory is something that's really difficult. But this is, again, something that quantum gravity makes really easy, and you can make predictions using that.
Yeah.
Even beyond physics, in math, there's been a lot of impact that's come from just trying to understand the math that's come out of string theory. There's remarkable facts that have been inspired by string theory. There's a whole field called string math at this point, which just does this. So just the remarkable number of connections that it's been able to make is already, I think, enough to put some amount of weight to it. But I personally am interested in it. Okay, I'm not even sure I should be categorized as a string theorist, because no paper I have written has done an explicit like string amplitude calculation or something like that. Okay, so I'm not even sure I should count as a string theorist, but I've certainly learned a lot from string theorists, and there's a lot to be learned about our universe from string theory. Even if we haven't solved all the problems, there's still insights, there's qualitative things, there's quantitative things that have been learned from trying to understand things in the language of string theory, and that's why I think it's valuable.
You work in quantum information, not the string theory, so it's kind of
I work in quantum gravity. I mean, I'm not particularly married to string theory. Okay, so tomorrow if someone comes up with another
relative of string theory,
like quantum gravity, so here's how I put it. Like quantum gravity is the problem. Okay, so we understand the problem. The problem is trying to put together gravity and quantum mechanics. String theory is an approach to it. And string theory has many other aspects as well. As we say, there's string math, there's quantum field theory, theoretic aspects to it, and so on. And all of that is valuable. The problem I'm interested in is trying to understand quantum gravity and what we can learn about it. And I would apply any tools that are available to me for that. And string theory is certainly part of it, but also other ideas. I don't know if the loop quantum gravity community appreciates this, but many of these quantum information ideas that we've been able to apply to, in the context of ADS-CFT, which comes from string theory, are you could think of as being inspired from loop quantum gravity. There are these things called tensor networks, which many people use in condensed matter theory and quantum information theory to represent quantum states. And this tensor network you should think of as some sort of discrete version of geometry, roughly speaking. It's sort of, you have a continuous geometry, but you discretize it in some way. And that discretization is a representation of the entanglement in a quantum state. This is how condensed matter people use it. And it turned out that this idea was remarkably useful in trying to understand the entanglement structure in ADS-CFT. And if you think about it, it's this discrete space-time picture is actually very similar to ideas that loop quantum gravity people wanted to promote. And I'm not sure that sociologically they understand that that has happened. Like if humans are, of course, flawed people, and if we were just with the single motivation of solving this problem, then we would apply all tools that are at our hand, and we would just we wouldn't have biases and stuff. Then we would just see that all of these things are maybe different facets of some of the same thing. At least they have something useful in them. And some people who were part of the loop quantum gravity community that I have worked with, for example, Don Marolf, who also wrote papers in that field earlier, have come to adapt ideas from string theory as well. And I think those are sort of the most remarkable minds who have figured out what is useful in each of these ideas. And that's what we're after. So that's why I don't like to call my field string theory, even though my department in TIFR is called string theory and most people do string theory. I still think that quantum gravity is the right word for it, because that's the problem. And if tomorrow we realize that string theory is sort of doomed to fail or something like that, I would happily give up and continue doing quantum gravity. Okay, so that's my identity. I apply tools from quantum information and so on to it, but I still think of myself as a quantum gravity person.
Yeah, so string theory is kind of a tool.
Yeah, I mean, it's like, I mean, it's just that string theory is, there's so much work that's gone into it. It's sort of like calling someone, there are all these theories. There were, before the standard model was existed, or even now. I mean, even for beyond the standard model theories, there are many candidates for dark matter, right? But no one calls themselves, I'm an axion person, or I'm a primordial black holes person.
Yeah.
Like it's a theory. If tomorrow you realize that it's not true, you don't lose all your validity. You can work on something else. Like that's the sense in which I feel like quantum gravity is the correct thing. Yeah.
So just like Hamilton's, and like someone can call I'm a supernova guy, and I can find through BO and cosmic chronometers. But at the end, you're just trying to find the Hamilton's, and just trying to understand how everything is expanding.
Unfortunately, since humans have, sociological identities, and they tend to associate with groups and tend to call each other by names and so on, it tends to happen that, we give monikers to people where they're like, okay, this guy is a this thing and so on. But, I still think that, everyone is interested in solving this problem. And that's the thing that unifies us. We can always find things that divide us, but I think this is the thing that unifies us.
Yeah, because there are types of people I have seen. One, like, because of because of this internet, people have created videos. So there is an image in students and general public that our goal is to have a theory of everything. But what actually physicists are doing, they are trying to solve one problem at one time, not like having a theory of everything.
Yeah.
So this should be goal to try to solve problem rather than there is a goal कि भाई हमें एक theory चाहिए जो सब कुछ समझा देगी at the end.
Correct. And that's a very long term goal. Of course, मतलब सबके मन में है कि we will solve this big problem, but of course you do small steps and move in that direction. And as I was saying earlier also, there's different ways people think about things, and it's useful to have many approaches because it's a difficult problem and you want to make some progress on it, and progress can come from anywhere.
Yeah.
So it's kind of useful to have that. Yeah.
So, we started with Einstein because, part of what made him great was not just he got the right equation, but he gave us a new theory to understand the reality. So I want to ask about AI in the deeper sense. We
Yeah.
have been talking about AI. You just open Twitter and you get lots of people solving equations, someone
Yeah.
solving,
Yeah.
Herodotus problem.
Yeah.
So, can AI give understanding or, only answers?
Yeah, this is a very good question, and I think it's a burning question. So, this is, जैसे you said, this is a very important question कि AI in today's world, how ये कैसे impact करेगा हर चीज को. तो मैं पहले अपना पर्सपेक्टिव दे सकता हूँ of how I have seen it evolve. तो 2023 में when these things were really picking up and ChatGPT really picked up, I was very skeptical of it. A lot of my friends, by the way, I was in Berkeley, which is in the Bay Area, which is tech hub, where बहुत सारे लोग move कर रहे थे to this field. Some of my best friends work in this field and so on. So मैं तब थोड़ा skeptical था, मतलब मुझे फिर भी लगा कि okay, मतलब सही है, मतलब इट्स डूइंग समथिंग इंटरेस्टिंग, वील सी हाउ थिंग्स प्रोग्रेस. एंड इनिशियली मुझे फिजिक्स में उतना यूजफुल नहीं लगता था. मतलब मैंने ट्राई किया था फ्यू टाइम्स टू लर्न समथिंग, बहुत ही ऐसे रोट सा आंसर देता था, नॉट नॉट पर्टिकुलरली यूजफुल. Over time, I started adapting it more and more. And initially, what it was useful for me was जैसे math literature survey करना. मतलब बहुत बार ऐसा होता है कि physicist को कुछ math का tool use करना होता है, कोई theory होगी या कुछ होगा which has been discovered by mathematicians for completely arbitrary, मतलब कुछ other reasons. But it will be useful. This is the beauty of math. Ki, every time I want to solve some problem, often I realize ki 50 years back some mathematician did this in some other language, right? So that's where it was very useful. Ki it sort of helped identify where to look. It was a much better version of Google. But over time, like I would say last year or so, it started getting remarkably good. And I mean, one of the things I remember was the first time in one of my papers, it helped. Well, it was some simple thing I could have done myself. It was a problem, but I just tried it on that, and it did a very good job at solving that problem. So that was the first time I saw कि okay, ये खुद से कर सकता है कुछ. And since then, it has just gotten better and better. Like every upgrade has gotten better and better. Now, in practice, when I'm in my office, when I'm not having a meeting with other people, बहुत बार ऐसा ही होगा कि मैं अपना कुछ काम कर रहा हूँगा एंड हर थोड़ी देर में मैं साइड में कोई प्रॉम्प्ट डाल दूंगा चैट जीपीटी पे या कुछ जो मतलब समथिंग अबाउट माय थॉट या कुछ काम करना है कुछ ऑफन जो मतलब व्हाट वी कॉल ग्रंट वर्क, मतलब जो मेहनत का कुछ काम है जो मैं आधा घंटा लगाऊंगा तो कर सकता हूँ तो कर दूंगा, पर वो मैं उसको साइड में चला देता हूँ कि वो चल रहा है, मैं अपना कुछ कर रहा हूँ साइड में. या फिर समटाइम्स जब मुझे कुछ आइडिया रन थ्रू करना है किसी के, मतलब ऑफन हम अपने कोलीग्स के साथ करते हैं कि कुछ आइडिया बाउंस ऑफ किया किसी के ऊपर, दे मे हैव सम फीडबैक ऑन इट एंड यू लर्न समथिंग. तो वो एट दिस पॉइंट काइंड ऑफ एक कोलीग जैसा फंक्शन कर रहा है, एक ग्रेड स्टूडेंट जैसा भी फंक्शन कर रहा है, इन द सेंस कि मैं उसको कुछ काम दे देता हूँ, वो करता है ऐसा, नॉट ऑलवेज करेक्ट, थोड़ा फीड मतलब बैक एंड फोर्थ लगता है टू मेक इट करेक्ट, बट इट्स जस्ट मच फास्टर. हाँ मतलब इट्स मच फास्टर, नॉट इवन डम, आई वुड से कि रीजनेबली स्मार्ट स्टूडेंट, मतलब नॉट न्यूबी इन द फील्ड. हाँ मतलब आई वुड से कि इट कैन डू अ लॉट ऑफ थिंग्स. तो नाउ इट इज इन अ वेरी इंटरेस्टिंग स्टेज जहाँ पे वो बहुत यूजफुल होने लगा है. और ये आई थिंक मोस्ट लोग ये बोलेंगे कि यूजफुल होने लगा है. तो अब इट बिकम्स अ क्वेश्चन ऑफ कि हम इसका क्या करें. मतलब जैसे ऑलरेडी we see around the world, we recently OpenAI came up with this thing of 10 problems that they've solved using their internal model. And ऐसे बहुत examples है of Jacobian conjecture being disproved and things like that. तो ऐसे बहुत सारे examples है of how it is getting useful at solving really new things. And even physics papers have been written on something being discovered using chat gpt and so on. So it raises a lot of ethical questions in the first place, but I myself find it, it's a double-edged sword, as you know, all of these technologies is double-edged sword. So let me just say what I think about the pros of it. The pros of it are this kind of thing where in principle this technology can free up a lot of bandwidth for research to go in a sort of faster way, because a lot of these things that we would give, like would have taken us a longer time, it can do just much faster. And it can do it on the side while I think about some other thing. Just if you think about like some very utopian world, then I just often give it something to do, and then I play with my daughter for a while, and then it's done by the time I just get back, and it like makes my life easier, that kind of thing. um, at the same time, it sometimes gives new directions you can think about, that kind of, like, maybe new insights that you weren't thinking about. So it's like having a good colleague. Now, if this technology is widely distributed, then you could imagine that this benefits a lot of people, in the sense that मतलब जैसे कोई यूनिवर्सिटी में कोई है जिसके पास कोलीग्स नहीं है जो उस फील्ड में काम कर रहे हैं, तो उसके पास चैट जीपीटी तो है बात करने के लिए, एंड इट माइट ब्रिंग आउट द बेस्ट आउट ऑफ दिस पर्सन. So that's like one way in which it can benefit. The downside is, so exactly इस चीज का downside है, for the first thing was कि once, मतलब मैंने 10 साल काम कर लिया इस फील्ड में, मैं या एक स्टेज तक पहुंच गया हूँ जहां मुझे काइंड ऑफ पता है क्या चल रहा है, और मैं सीख चुका हूँ जो मुझे सीखना था, और अब मैं सॉर्ट ऑफ उसको अप्लाई कर रहा हूँ.
Yeah, you can look at the problem कि से भाई ये तो गलत हो रहा है.
Yeah. And I have some sort of intuition for it. Like, we build a lot of our intuition using problems we've solved, and so now at this point I don't feel a lack of what should I work on. I don't feel like I have a lot of ideas and I want to work on them, and I don't feel a lack of it. But the more and more we start giving up on our thinking, like in some sense I'm like, अरे हाँ ठीक है, चैट जीपीटी ये कर लेगा मेरे लिए. So since I haven't gone through that process of thinking through things, it's possible that someday I will feel like I'm losing some of that intuition that I had gained. That
Yeah.
is one of my worries.
वो फिजिसिस्ट का जो एक काम होता था वो तो मतलब क्या पता गायब हो जाए, वैसा वाला एक डर लोगों के
तो
बीच में.
वो तो पता नहीं, मतलब वो हुआ तो फिर तो मतलब lot has probably changed in the world, so I don't know what to say in that situation. But but even at a much more local, मतलब shorter time scale, what I think of is कि I'm not sure about earlier stage people, so graduate students, bachelor students who are interested in getting into physics. What's the right way for them to go about it? Because I think there is a sense in which it's a tool, so you can use it, but of course you can use it to do all your homeworks, and you can use it to just never actually go through that process of learning things yourself, where you just feel like you learn things but you don't actually learn things. उस टाइप का process भी हो सकता है, which won't get us anywhere, and that would be really bad. That would be it would hurt us. So I'm not sure exactly how to navigate this. I'm still trying to figure it out. I mean, I have a 1-year-old daughter, so I'm still figuring out how education will work in this AI world. So it's really something we have to think about very, very, very carefully. Because, as you know, anytime any technology comes, we tend to use it and it becomes very useful in some way, but we also tend to lose skills associated with that. मतलब my generation will know phone number सबको याद रहते थे बचपन में, आज मुझे किसी का भी phone number याद नहीं रहता, मुश्किल से अपनी वाइफ का याद रहता है. तो और मैप्स इज अनदर एग्जांपल where directions पहले सबको पता होते थे, और now who knows कि क्या
Movies about
directions है, so you
those,
often
movies
forget.
about them कि खजाना ढूंढने जाना है मैप का यूज करके.
Yeah, exactly. So that's one thing we'll have to keep in mind. How this affects the research environment in particular is something I'm not sure of. There's, as we said, like, there's definitely some. Okay, here's another thing which I'll say specifically about quantum gravity. Quantum gravity has really lacked from the existence of experiments. As you know, it's a very hard problem. So we don't have experiments that really probe the Planck scale, or any kind of quantum gravity really. It's really difficult to build an experiment which does that. So in the absence of that, maybe this could be a boon in the sense that ये हमें it serves as an oracle almost, कि मतलब sometimes maybe it gives us an answer which then it's our job to figure out if that's the right answer, or like maybe it gives us some inputs which lead us in the right direction. But at the same time, when I'm working using AI, I have already gotten to a point where I think the word people use is slop. There's a lot of AI slop. तो it generates so much. इतना सारा उसने बोल दिया, उसमें से मुझे हीरा निकालना है. मतलब उसमें कहीं होगा छुपा हुआ, बट निकालना तो मुझे है ना. तो वो बहुत चैलेंजिंग होते जा रहा है. And मतलब basically the whole skill set is sort of evolving. Whole skill set will change, I think. I think कि मतलब one thing that's becoming clear more and more is कि ये जो grunt work, मतलब tedious things करने का एक skill था. मतलब so there are kind of physicists where what they can do is like very complicated calculations and you're like कैसे इस बंदे ने ये सब किया, pieces together a lot of things, very long paper with a lot of calculations and stuff. It's मतलब for a human to be able to do that, वो skill शायद चला जाए. It's similar to जब मैथमेटिका वगैरह एंटर किया as a program, people now don't have the skill of knowing solutions to differential equations and stuff.
Even
Like
knowing the
I don't
graphs
know
of
most.
equation.
Yeah, I mean, you just put it on Mathematica, it'll solve it for you, right? So who cares about the classification of some differential equation, whatever? If it can solve it, it'll solve it and give you the answer.
The same
So
evolution is happening.
this, yeah, so skill set is definitely evolving, and I think this particular skill set of really being able to do very tedious calculations and stuff, it is of some value, because as I was saying, you build some intuition using that, so that will be valuable, but as a research skill it won't be sufficient, I think. I mean, I think it'll become a little bit obsolete and most people won't have that skill. Unfortunately, as far as I can see, this is something that India has traditionally been very good at.
Mathematics.
And mathematics, and even in theoretical physics, like a lot of these like intense calculations and very mathematical this thing. A lot of like these complicated calculations and stuff. I'm not sure that will stay as relevant in the presence of something else that can bear all the grunt work and do it. It may be that we will have to evolve to something different. And what that skill is, I think we'll only figure out with time, because even this is such a fast moving field where every new model has new things it can do, new capabilities and stuff. So we're still trying to figure out what it can do. And I think everyone is trying it in their own way. But okay, there is no doubt that it's going to be useful in some way or the other. But I think we'll have to navigate it carefully. Especially for education. I think कि teaching में उसका बहुत ही हमें careful रहना पड़ेगा कि how new students are trained, how do we make sure that they're not just like we don't want students to be all fluff, like we want there to be some substance.
Because everything is changing and syllabus is still being the same.
Yeah, so we yeah, exactly. Yeah, this is something I've been thinking about a lot, about how things will change, and I'm not sure if anyone has a good idea to it. But I just wanted to put in my thoughts about how it's been benefiting me. It's certainly been benefiting me. One more issue that I think of a lot is about the availability of such things. So, already Chat GPT has a free version, a paid version, and a pro version. This pro version costs about $200 a month, and $200 per month means 20,000 रुपए. तो 20,000 रुपए काफी ज्यादा है. हाँ, तो and the others have some version of this type. मतलब order of magnitude similar है, 10,000
I mean,
20,000 ऐसा.
20,000 is the salary of a normal, lower middle class family.
Exactly. So it's going to really damage the economic fabric, I think. Because this is a great enabler, of course, and as I will vouch to it, I think the pro version is much better than the other versions. So eventually it's going to hurt people who don't have access to this. And so you can imagine a situation where it's even worse, like right now, Anthropic, OpenAI, Google, they have some small set of teams who have access to their internal models, and they can do whatever they like. And just they said they've solved these 10 problems they claim to have solved, and so on. You can imagine some situation where this will become a bubble of people who have access to these things, and only they can solve these problems. Everyone else in the world just, sits and watches and claps while they do that. That would be really sad. And I don't want the world to go that way. I would like somehow for these things to be open access. How we make that happen and how we ensure, it's not just limited in some way, in such a way that it just, exacerbates, for example, gaps between the developing and developed world. Like, you don't want that to happen. I don't want that to happen. Um, it would be very important to see how we navigate that. On that note, it's also very important for that reason for India to develop its own powerful AI. Like China has been doing that. China has been doing that really well, and India needs to do that. I mean, it'll have to catch up on that.
No matter what,
Um,
we need to do that. Otherwise,
yeah,
actually,
no matter what. Like,
we have actually lost the war, but still we have time to develop to
yeah, I mean,
compete.
I think we can still do it. I mean, there are certainly other countries which aren't even close to it. I think India at least has the capability of doing something
Yeah,
like this, but it might be important for us to do that
yeah,
because it feels like the capabilities are growing very fast, and you could imagine a situation where this will just have tremendous amount of power, and we don't want to be in a situation where we're held hostage to that in some way, or we are losing because of that. um, I certainly hope that Anthropic and OpenAI are large-hearted enough to give open access to everyone. But the free market capitalism doesn't necessarily work that way. And
yeah. You need to create competition for the better future.
yeah, yeah. I mean, they may. It is true that India is one of the biggest markets, and so I'm sure that there will be some advantage to dealing with having a lot of Indians have access to these things and so on.
Because
But
recently we have got the free Google AI Pro because of that.
yeah, yeah, exactly, exactly. I mean, one example that I think of often is sport. Like, in sports, you can think about the Olympics, where Olympics are largely dominated by rich countries, right? I mean, the US dominates most of it, and you could be like, it can't possibly be the case that these people are the best at all sports, and so it's not possible. But I think the difference there is often resources. It's
Yeah,
what
training,
resources you're putting in and the system, the training, all of the money that's going into it,
nutritions
the
and everything.
facilities, the infrastructure, all of that. And now that was true for sports, but now it seems like this is doing something like that for just the basic skill of thinking, right? I mean, it was always the case ki banda mehnat kar, Ramanujan existed, right? So that's kind of crazy that a guy in a small village just has access to some textbook and he just learns all of math from that, and
Yeah,
he like goes on to contribute like as like some of the most beautiful math that has been ever known. That will stop happening if people don't have access to these things, and it'll just become another sense of the, just like the rich becoming richer, it'll become that the rich become smarter or something like that, and it just feels wrong. And yeah,
yeah.
but this is all very new, and I'm not sure how things will evolve, but these are things to be that I worry about and that we should be careful about.
I think people will get access if this will become, more and more and more so. I think people will get
Yeah,
access.
but I mean, if you think about the military, so one analogy that people sometimes make, and this is the thing that's in the US was made a lot when thinking about whether they should, allow NVIDIA chips to go to China and so on. The analogy that was made was this is the new Manhattan Project. Right. And in the Manhattan Project, it's very understandable because it's a matter of national security that you want only a close set of people to have access to it. But if this goes that way, then it'll be like, everyone is just dependent on this one country. What ended up happening in that situation was largely that there were a few nuclear powers, and then everyone else was, at the behest of them in the Cold War to protect them. And I don't want that to happen for everything. Like it shouldn't be that for the simplest of things, if India has to do something internally, they rely on US systems to do that or something like that. Like, eh, it may not be this way. This is sort of a dystopian version of it, but these are the things that one may worry about, at least from an Indian perspective. This is the thing I think about from an Indian perspective.
We need models which are built in India. We talked about renormalization. So,
Yes.
modern model can maybe work on normalization.
Sorry, the models can work on renormalization.
Yeah.
Um, yeah, I mean, the models at this point can do a lot. I mean, so what
You
they're
said कि
really,
infinity is
yeah.
doing the long calculations होंगे.
Yeah, yeah.
वैसे
So in the context of quantum gravity, this non-renormalizability issue was something people tried to solve in the language of what people had used in standard quantum field theory earlier. This was just what people try to do is basically find some other theory from which this arises, and then once you have found that complete theory, then you would have solved the problem of non-renormalizability because that theory is renormalizable, and once you fix the parameters of that theory, then everything can be predicted. This is how it happened for the nuclear forces. Now, with gravity, people have made that attempt. It's a program called asymptotic safety. Um, and I don't think it has quite succeeded so far in my reading. And there seem to be hints that gravity seems to be different in the sense that it needs something else to complete it, not just the framework of quantum field theory. And so that's why these ideas like string theory seem useful, because it feels like you have to go somewhat beyond the standard quantum field theory. One hint of the fact that you want to go beyond standard quantum field theory is this idea of holography, the idea that you really have to describe theories in one less dimension. That is just not how quantum field theories usually work. In the context of gravity, just because quantum field theories don't work in this way, where you have one less dimension, this feature of holography seems something special to gravity. It seems natural that the same ideas that solve this renormalizability problem wouldn't solve the problem here. And there are good hints of this. So there is this theory called supergravity, which seem to be renormalizable. And like when people did perturbation theory, they didn't hit this problem of renormalization until a while, but then eventually there was some crazy very complicated calculation that was done which showed that okay, eventually you hit that problem. And so it was really a check for this fact that it seems like this quantum field theory framework might not be sufficient to describe quantum gravity. So so even with these models, like we would want something like that, where if it can point us to aspects of this other universal theory which can solve this problem of non-renormalizability. Like we think we really need a new framework.
because Dirac didn't like this normalization thing.
Oh, but renormalization, I mean, I would argue that within the framework of quantum field theory is like is firstly pretty well accepted, and also I would say like one of the best insights that we've had in the last century. Like this was the insight by Wilson which explained how renormalization works. It's a beautiful idea. It's this idea that you can have some degrees of freedom at some distance scales, and when you look at it from outside, it can look certain slightly different, and it looks like these coupling constants that show up in the problem can evolve as a function of how much you zoom out of the theory. And that was a remarkable idea which he explained in some nice examples, and it sort of made sense of all of these funny infinities which were showing up and so on. So the idea of renormalization per se will, I think, last. I mean, that's going to stay. But the fact that gravity is a non-renormalizable theory, something peculiar about it's just because we haven't figured out the complete theory. So when one says that something is a non-renormalizable theory, the modern way of understanding it is that it's an effective theory, meaning that if I look at only energy scales that are low enough, so if I do experiments like at real world energy scales and so on, then Einstein's theory is a good approximation to it. And you can systematically include corrections by doing more experiments and so on. But if you want a complete theory, then you're asking for more, and this may not be a complete theory. So you will see that as you go to higher and higher energies and you hit this problem of non-renormalizability. That's sort of a signature of the fact that you don't have a complete theory.
Yeah, so exactly. So there is this tube I'm reading currently, I can say on the screen.
Yeah.
So this is saying that frankly, AI is not at the stage where it can do theory building, perhaps a crown jewel of math. But who starts their career by building a theory? Most their careers start with solving problems, understanding the limitations of theories, growing sensitivity of hunch about the
Yeah.
right structure, and only then some are lucky enough to come with interesting theories.
Yeah. Yeah.
Uh, so do you agree with this, or like do you have any thoughts on this?
Yeah. I mean, this is related to my thought about what I worry about graduate students because, like, of course, like when it takes years and years to become an active researcher. And the whole skill that one develops as a PhD student is understanding which problems to solve, how to attack them, how to, build a taste for what should be solved, what can be solved, and so on. And the way you do that is by really, first understanding the literature well, trying to solve some problems, failing at it. Yeah, if you fail at things, you get a setback. Your advisor guides you through it. They tell you to do something. You learn something, so it's you sort of evolve in this trajectory over time, and it really takes like an entire PhD to even get to a point where you can do independent research, and let alone build theories. Like when we say build theories, that's like a very tall task. There's only few people who ever like build the biggest theories that explain everything. But on small at smaller versions, everyone makes their contributions, and those things sort of lead to bigger progress and so on. But I think Mankey there makes a very good point, which is that it's like y- I mean, it's this fact that it's an evolving stage in some sense. The one more thing, the way I think about it is, if you look at the later half of that tweet, he says that. Um, you the people who stick to what they thought was their skills in the past will tend to die out. Yeah, we may stay in the past, meaning that this is sort of a new era where skills will evolve. What is a skill will evolve. Like maybe what people used to appreciate 20 years back will just not stay a skill. Like people will be like, okay, who cares about that. So we have to really find what's yeah, we will have to figure out what the right things to do are. What is the uh, like I had this there was this analogy I had thought about at some point. So there's this famous story about the race to the South Pole. So the Norwegians and English raced to the South Pole, like who could get there first. And the English had a very different set of rules in their mind. Like they imagined that what they wanted to do, it was actually very noble, which was they wanted to have a whole scientific team go along and do it in some way where it would be valuable and so on. And the Norwegians just wanted to somehow get to the South Pole. Right, their only goal was get to the South Pole. They were just playing that game, and eventually they won. And today, like people remember in their textbooks that Amundsen was the first person who got to the South Pole. No one knows that this second team was trying to get there in a noble way, and they lost that race. And I feel like we're somewhere there where it could be like people are just playing different games. This, for example, the skill of maybe being able to completely memorize something, or being able to write down 100 equations and do some very complicated calculation may have been a noble thing to do, but maybe it's just not the game we're playing now. And maybe we'll have to all become like explorers and just find new things. Like the skill may just be asking the right question or something like that. Like, when I think about what was the great thing that Columbus did, like he probably had some logistic things he had to figure out, but all he did was, shoot in some direction. He was like, okay, let me go in this direction. He found America. And maybe it'll become like that. Like maybe we're all supposed to just ask the right question, and then we'll just, hit some jackpot. That may be how skills will evolve, and maybe people from 20 years back will shun that by saying, oh, you guys have it too easy, or you don't have all the skills that we used to have back in the day, or something like that. But that is going to be the new stage, and that will be like the new great physicists may end up being the ones who have that skill. They may not have the same skills as what someone had 20 years back. And this may be true forever. Like, maybe when writing was not as common, maybe the smartest people then were the people who memorized like as much as they could. But once writing became a thing,
In Indian history, writing was not that famous. I think the vocal part of was more
exactly. I
famous.
mean, India is a classic example of this, where, even things like the Vedas were carried over generations just by rote learning. And that was, a skill that's been looked up to, and arguably that has stayed in the Indian education system for a long time. That just stopped being a skill at some, yeah, and that just stopped being a skill at some point. And okay, maybe today some kid comes and he can like recite the whole Rig Veda to me. I'll be like impressed, but it's not going to get him a job. Like, and and we've got to figure out that. Yeah.
Yeah. So you said that good question. So how decide something is a good question and something is not? It's a very
I don't
difficult
know.
thing to.
It's a very difficult thing. As I was saying, like it really takes an entire PhD to even get to that stage, and not everyone even gets to that stage. Um, it takes a lot to ask the right kind of questions. Where it's very easy to ask very easy questions. Where okay, after some amount of training, you can always ask questions which can be answered very easily. It's also very easy to ask too hard questions, like where you're at some pop science level, where you're like, oh, what is the Big Bang, or
What
something
is
like that,
before the
some
Big
very
Bang?
broad question.
Yeah.
Yeah. And the hard thing, which a researcher develops through their PhD and through their career and so on, and which is the non-trivial thing, is to ask questions which are in the sweet spot, which are not too hard, not too easy, but still interesting enough, but still answerable, something like that, something where it's in between. And that it takes people decades to really get to that point, and not everyone even gets there. And so there is some real skill in that, and it's a non-trivial thing that we as humans have developed. At least some humans develop it over time, and as a system we've managed to get some people developing that skill. And maybe we will have to really poke into what it is that makes that happen or something. But I feel like it really comes from experience, and which is my worry about where will the new Einsteins come from. Like how will the graduate students be trained in order for them to be skilled at that thing? Maybe they will do it on their own somehow, but we may have to give it some conscious thought.
Even questions like what was before the Big Bang, those questions come because
Yeah.
people have trained over the let's say 100 of years from Hubble to today.
Yeah, exactly. So I think it's going to be very interesting, but also it's a little bit scary. Like I don't know how things are going to evolve. So
Yeah.
it's yeah, we'll see how things go.
So what were the problems you would like to solve in the next, like you really wanted them to
Yeah.
solve?
Yeah, this is another interesting question, because when I try to answer the question of what are problems I would like to solve, as I was saying, I try to think of this sweet spot where I'm not just saying something which is like so hard to solve in the next few years that that it can't be solved. I want to say something which really I think can be solved. But this, of course, is a function of the tools at hand, right? I mean, when experimentalists say what they want to observe, they won't just tell you they want to observe Planck scale physics, because there is no tool they can build which will do that. But we here have a tool at hand which is so fast evolving that maybe it's going to give us access to things that I didn't have access to. So it's a little hard to even say what are the kind of problems I'm going to be trying to solve. I think the only skill right now is to sort of stay open in the sense of what kind of questions you'd like to answer. There are, of course, a lot of broad questions in quantum gravity, for example, trying to understand the black hole information puzzle, like what really happens when you fall into a black hole. This is something that we've made a lot of progress on, but we've not completely answered this question. There are other kinds of questions that we'd like to understand, like, for example, beyond the standard model physics. I mean, not just from quantum gravity perspective, just theoretical physics in general.
Yeah.
Can we somehow narrow down what dark matter is, or
Hamilton's problem.
the Hubble tension, I'm not even an expert on this, so I'm not even sure if it's a tension, because like it could be that it's some experimental thing. I mean, it could be pointing to new physics in the sense of a new theoretical physics. It could be that it's a problem within the experiments, like maybe one of the
Yeah,
experiments is off from the other by some systematic reason. But either way, it could get resolved in that way. It's
maybe we are not
something I
able
don't
to
think about,
see
but
the relation
yeah.
between data and the questions.
Yeah. So I think the main thing is that what is an answerable problem might also evolve a lot in this short period of time, and so we'll have to adjust to it. I mean, there are obviously a lot of big questions within quantum gravity. Um, like, I mean, as we were saying, like it's easy to ask about the Big Bang, physics before that, the multiverse. The multiverse, I think, is a very interesting concept, and we'd like some ways to really test it, or if we can even learn something about it. Like, for example, in string theory, there is this so-called landscape of string theory, which is all these different solutions to string theory, which all look like different universes with different properties, like different coupling constants, different masses for the different particles, and so on. If we could somehow even learn something there about how likely it is to see something like our universe, those kind of questions are would be amazing if we could make any headway into that, because eventually what we want to answer is, why do we see what we see, and why is the cosmological constant so tiny, and these kinds of questions will be very interesting to see if these are usually very complicated problems, but as we've seen, AI is able to make headway in often what seem like complicated problems. It's the kind of problem where it can make progress in, where it's like a very complicated function which is trying to approximate, and then it's able to make some progress there. So we could see some advances in those kinds of questions. And so I think what's going to happen is we'll all have to sort of refresh and keep thinking about new questions that may now get answerable, in order to sort of stay relevant, stay at the forefront of research. So I think the research frontier will change a lot.
Exactly. I think we have talked a lot about string theory, quantum gravity, and AI in the current scenario. So now you are back to TIFR. How is the life going at TIFR?
Oh, I absolutely enjoy being back. So I got back to India earlier this year, after spending about 10 years in the West, like in the US and Canada. And I personally really like being back here. I grew up in Mumbai, so I really love being in Mumbai. And the research vibe at TIFR is fantastic. So I really enjoy being there. Like the string theory group is amazing. The entire research environment is very good. Um, and so it's been really nice being back here, and it's also given me a sense of purpose in some sense. Like, in the US, things sort of work. I mean, those are the places where systems have been established for a long time. You can make some small contribution here and there and whatever. Like they've been working like that for decades now. Um, and in India, there's a lot of scope for growth, and there's just so many different ways to contribute. So I feel like it's very valuable, and I'm not the first person to come back to India for research. Like there's so many great people who came back, and they've sort of set a precedent. So it's really attractive for Indians in the US who are working in these fields to come back and work for work in this field and contribute to Indian science.
Yeah, recently Raghu Mahajan came to join
Yeah, Raghu
ICTS.
is Raghu is one of the recent people, and Raghu is a close friend, and he was also another person. Like we used to bond a lot over the fact that both of us eventually definitely wanted to move to India, and both of us are pretty happy being back.
You joined the string theory group of TIFR. So how is it like to work with Siraj? Because I did episode with him. The first episode was with him. And when I started to talk to him, I was like, oh my God, this is something I wanted to hear from a long time. This is how you explain things. I was like, oh my God. Something like, Feynman has born again in the country.
Yeah, Shiraz is magical. That's definitely true. I mean, he's certainly. Um, I mean, there's some people I've interacted with who, like, whenever I spend time with them, I learn something. There's a few people like that I have met in my career, and Shiraz is definitely one of them. And it's just amazing being around him because, firstly, he has incredible amounts of energy to just, he's just so passionate about physics and so passionate about everything. So it's really nice being around him for that reason. He's also someone who's very passionate about India, per se, so about Indian science, and that is also very inspirational for younger people who want to come back to India and contribute to India. So it's definitely very nice having him that way. Um, and he has been really nice to me, like, for example, for giving me a position here and so on. So he's been very supportive of my move back to India. But just physics wise, he's just amazing. Like, he's like a one man army or something. Like,
Yeah,
he can just conjure up the energy in you,
yeah.
for
You will not
just
get
bring out the
bored.
best in you. Yeah, I feel like he brings out the best in everyone around him. That's really the strength that he has. Yeah, you would never feel bored. There's not a moment I feel bored at TIFR, because there's always some sort of interesting discussion that's happening. There's always a lot of passion in all of these things, and it's always like. And I'm always learning new things, in the sense that he lived in an era, like, he was a graduate student in an era which was also very exciting for string theory. It was basically the time when ADS-CFT was being developed and so on, and so I get to learn a lot of different perspective from him, because as in the US, topics tend to trend, and the things ebb and flow a lot.
Yeah,
Like, things come in fashion and things go out of fashion and so on.
trendy.
And yeah, it's trendy. India tends to be more constant, in the sense that people sort of stay in one field and sort of really want to, you know, uh, be excellent at that one particular thing, and really get to the depths of it and so on. So while I was trained as a graduate student in the US, I was trained in a very different way from when he was trained, and so we have very complementary views. And I learn a lot from him, based on the fact that he has all these perspectives. So there's definitely that. Plus, his just energy makes you want to learn things. Like, for example, seminars at TIFR are the most fun that I've ever had anywhere, because there's always so many questions. There's so much discussion about anything. Like, the first time I gave a seminar at TIFR, I felt like, I mean, I was working on some topic which I didn't think anyone else there was working on. So I thought, okay, I mean, they'll be like kind of interested, but not much. But they actually asked a lot of questions, and it was very vibrant, because they're just so interested in physics, no matter what, like, just anything
Well,
physics.
was that a seminar where someone mentioned junior people like Witten, if I remember correctly?
Oh yeah, that was Shiraz.
Yeah, I remember that lecture.
Yeah, that was my talk.
Yeah, yeah. That was actually funny because I was not going to watch that whole lecture, but when I heard that, I was like, let's watch it. Let's see what is coming.
I was hoping that wouldn't get popular, but yeah, he
Yeah.
he was pointing out that Witten wrote a paper that was that cited my work, and talked about it, and so he was just trying to be nice to me.
Yeah, I talked to a PhD student who was giving the interview of TIFR, and he
uh,
told me the most of the people who take interview asked you the mathematical kind of questions, but Siraj, more
uh-huh, uh-huh.
empathize on, imagine the physical picture of that. So
Yes,
he
yes, yes.
does not rely on mathematics. So that was,
Yes, yes, actually, this is certainly true. Like, one of the things that's lovely about him is that, firstly, he's very strong at a lot of math and so on, but his motivation is always physics. I mean, he always wants to ask very physical questions, and answer them. So it's sort of a very interesting um, complementary perspective that he himself has, where he is very strong at math and he can really,
yeah, hydrodynamics.
talk
He
in that
knows a lot
language.
about.
Yeah. Yeah, but he's really focused on physical questions, and he understands when something is just math for the sake of math,
Yeah,
versus when there's some physical point to be made here.
yeah, exactly. So I think we had a really great conversation about lots of things. I hope you enjoyed the conversation, Pratik.
Yeah, I definitely did. Thank you so much for having me. Yeah, thanks. It also got me to think about some of these AI things, because I mean, it's something that is affecting everyone's life, and I certainly had to put together some of my thoughts on this thing, because there's just so much about it.
Yeah, thank you for joining us today.
Thank you. Thank you so much, Ayush.